So, introduction to BGP, the ultimate tech that is built a long time ago. Things just haven't changed. So, who am I? First of all, I'm Gideon, or known as Gideon online, or in person. A first year RITSEC major. I do blue team and black team, like systems administration. I really, well, I've worked in education for a decent while. Middle high school type stuff, and doing systems for that. Also with nonprofit work, and I was introduced to networking at a very young age. Now, as far as BGP goes, networking, a couple of quick things to go over for, four bits of vocabulary concepts you need ahead of time. An AS, which is autonomous system. Think of an ISP or large network. You have the subnet. People get prefixes and subnets. People get very scared about that. We're going to deal with two of them today. Pretty much all today. /8, which means the last three octets, so the last two sets of numbers can change. And /16 means the last two sets can change. We're going to pretty much stay just with that. /24 is when the last one can change, and there are other numbers if you like math. A router. It's not the thing you got from your ISP. I mean, it is kind of, but it's a network device that it will take a packet from an internal network from another network and decide where it should go next. It's next hop is the term you're looking for. And up here, this term is actually very loaded in BGP for reasons. We're not going to be talking about settlement free peering, which just means free peering. Like I give you data, you give me data, we don't pay for it. We're just going to say peer is just two networks that are connected. Keep it at that. So, what is BGP? What does it do? It's the Border Gateway Protocol. Yes. It solves the main problem of how do you take packets from point A to somewhere point B across the internet. How do you decide how to get there? And it provides basically three important pieces of information: the prefix, or which network it is; the AS path, or the different networks it's going to go through; and the next hop, the next step. If I want to take that route, it's the next step I do to send this packet onwards. Also, with BGP, it communicates routes, but it's not packet wagon. It does not actually do the forwarding itself of packets. It just says where they should go. And also, the one kind of interesting thing to think about is that the routing plane of where BGP says things should go and the forwarding plane where packets actually go aren't always the same, which is a nightmare sometimes because it's hard to troubleshoot. So general operation of BGP, what does it normally do? First thing you do is you get various paths from your peers. Everyone broadcasts it to each other, they announce it, it's called, and then everyone sees the other peers. In terms of the best path, if have to get any network, you want to make sure you know what that is. You also have other paths you'll keep track of. You advertise the best path you have to go through you to all your other peers, particularly if that changes. And then you apply policies to change your preferred route. Particularly with things like load balancing and pricing. Like maybe you have a backup link that's expensive or smaller. You don't want to overload it or don't want to pay a ton of money. So you use policies. We'll talk about that in a minute. Well, let's talk about a BGP update message. This is from Wireshark because, let's face it, what else was it going to use? There's only 4 details you care about here. There is the fact it's an update message. That just means it's sending out a new route that's available. You have the path. You have the NLRI, which is just the prefix. It has some other details, but you don't care about them. It's the network you're talking about. You have the next hop, so it's the next place it's going to go to. So in that case, that's that router. Whoa, too far. And the AS path, which is the path of networks that you're going to be taking. You really care more about the length of this than anything else, because you don't want to take the longer path you don't have to. But also it's useful for analysis. I'm bad at buttons. So baby's first BGP. This is simplified, but so you have a network here, right? And you have these 3 networks, and 2 of them aren't connected at all, and we connect them, and we have BGP decide the routes. And so, if this works, there you go. See, packet goes from 0 to 1, and with an update message, and then 1 gets the route, and then it sends it from 1 to 2, and then 2 thinks about it for a minute and gets a route as well. And just those 2 steps, now router 2 can figure out how to get to router 0. And you can see the route. The packets are sent. This is from packet tracer, from the Cisco packet tracer, because again, it works. And 2 important details that the update message was sent. The first packet's on the left, just saying that hey, packet was sent, and then with new routes, and then on the right is also another update. And because of that, that happens. And on the other direction, because things might want to reach the other way, if this loads, oh Lord, let's do this thing called I undo and then I redo, and now it will work. Yeah, there you go. So there you go. So the packet goes from 1, and then back to 0. Gets complicated apparently. And then now all of them have the routes. And because of that, now any network on any other networks, so any other segments can be accessed from any other point. And that's how the internet works, but bigger. And again, the same kind of thing in the packet. You have the update message from the left is the first packet, right is the second packet, and those get sent along. And then you see now at the end, via all that process, we ended up with a routing table that actually gets you from anywhere, even though router 2 and 0 aren't connected directly. And that works on long distances. Doesn't mean a lot in this small setup, but it means a lot more and get things bigger. So why might you use BGP? Well, you, an individual, don't probably. It's a thing large networks use, and you can say multiple upstream ISPs. It's frequent. You might do your own BGP. You might also just tell them to do it, depending on preferences and other things. We're going to use Anycast. Anycast when you have one IP address in many places. Say Google's 8.8.8 for DNS. That's not one server. That's servers everywhere, and it's because that's a thing called Anycast. Basically, you have one IP address that has multiple places, and the internet doesn't actually really care if you have multiple different locations. It just figures it out because of BGP. It will say that sometimes for Anycast you have your ISP do it for you, but you have to work with your ISP. No one wants to do that. Or you're going to be able to control load balancing. But again, if you have the two links that you talked about earlier for pricing or for load balancing, or for bandwidth constraints, you might want to use BGP to kind of tweak the rules of what people want to do. Or you're going to do something really complicated network. People like doing that, and BGP does that. It gets very complicated very quickly. But now, there's actually kind of two things that go under the BGP umbrella. There's eBGP, or external or exterior BGP, and iBGP, which is internal or interior border gateway protocol. And so they're the same protocol but different uses. So for eBGP, if it comes from a pure different AS, different network, external. That I hope makes sense. And you can advertise to any peer, so there's no restrictions on who you can broadcast that route to. It's topology agnostic. That just means networking any orientation, like to the internet. There's no internet police saying you have to have your network in this correct way for eBGP. It just works. iBGP, it comes from has to be from the same AS. It's internal. I hope that makes sense. It can only be advertised to an external BGP peer. So you can't advertise iBGP routes to other iBGP peers. And that's because it requires what's called a full mesh topology, which just means everything's connected to each other. There are two small exceptions to that, but the photo of full mesh, the idea is everything has one link to everything else. You can get around using a full mesh by using confederation, which is like ASNs inside of your AS, using your AS inside of your AS. So that's really complicated, and usually actually is not what you want. And there's route reflectors, which basically means you have full mesh to certain routers, and those routers basically connect to each other. It's very similar to confederation that way, but both of those are very complicated, and we're not going into that. Other small differences: eBGP, the next hop, so like the next place you go is set to the local router. So when I say give you instructions how to get somewhere through me, you then go to next person. I tell you to go through me, not through the person I got it from. There are non-transitive attributes that are lost, so like local preference, because if you're going not locally, you don't care local preference. iBGP, next hop is preserved because it's full mesh. And if it's equal length, which is something that always kind of gets me at least, if an equal length BGP path exists, it'll prefer the external path. And that's because it avoids looping and other bad things. It makes things more stable. So let's look at some real routes here. Now this looks a bit overwhelming. This is from the Hurricane Electric Looking Glass. Although ISP is a Looking Glass, just Hurricane Electric's pretty cool generally. And so this might look pretty complicated. This is going from a server in Equinix to Railtel, which is a national ISP in India. Well, we first notice that all of these end in the same path, same ASN. That's because all going to 9829, which I detail as Railtel. So you're going to Railtel. That's helpful. But then also 3 of these are actually basically the same, they're taking the same path. But then why might one be picked over the other one? Because an AS is not the same as a route. Like, you might be taking more distance inside of one network and less distance inside of another network. And one of those is still better than the other one. It just happens to be that they're both networked. It's like going through countries. Like, you could go from Mexico to US to Canada very different ways, and one of them might be a lot shorter than the other. And the last one is just a backup link through Telia, or it's not Telia anymore. That we don't care about that because that's in Sweden and probably very far away. But if everything else shuts down, it might be quicker. Now one more we're going to go into is going from the route server that it doesn't have any visual location to 21 Vianet, which is a Chinese ISP or Chinese something. I don't remember. Doesn't matter. You see the top one, makes sense, right? You're going from the China backbone to ChinaNet. That makes sense. Second one, then you go from China backbone to China backbone. And the thing is that you're not actually leaving or entering itself. That's not how the internet works. You're actually, it's a way to cause other people to not prefer that route by making the path longer. And so by making it longer, because the route length is one of the most important metrics that's used, or one of the most important things that decides if you want to take a route or not. You take the longer. You can basically add it yourself multiple times to make it seem less preferable, but it'll still be there if, say, the first route goes down. Now, path selection. You have all these paths now. How do you pick which one you want to do? The first thing you do, remove all any invalid entries. Entries can become invalid because, say, like, you lost that connection to the next hop. So, if you can't get to it, then, of course, you're not going to want to use it. Also, if there's a more specific, so you pick the most specific route possible. So, like, let's say if you're thinking, that way you can have bigger groups and you care about the most specific one, which comes into play when it comes to security as well. And you set the highest weight. And the weight is a property specific to the router, just considered a preference, but they have different naming preferences because different scopes. And then you go to the highest local preference, which is across the entire AS. The shortest AS path, so the shortest path you prefer. You prefer external over internal. That's again different looping problems. And then lastly, the lowest multiple exit discriminator, which is a metric that's kind of we'll go into in a minute. It's just a number to say preference for now. Your communities, they're how you apply policies. If you are adjusting knobs on BGP, you're using a community. That's just the way it's done. In the usual format, you have the AS number, and then you have a colon and the community number. And then there are some policies and you apply policies per community. And yeah, these are the knobs you actually would be pulling if you were to be running a BGP network. You want to apply policy. You change communities, that's how that works. Now, let's say you want to announce your own routes, and you can. It has to be bigger than /24 for IPv4, so that's, again, the first octet can be anything, and the last 3 are set, or bigger than /48, which is 2 to 16 like local networks, essentially. Because it goes to 128. You be as general as possible. Don't do 10 things that could be simplified into one thing. So aggregation. Unless there's a reason you need to be more specific, you probably only need to announce one prefix. And also, we're already out of IPv4 addresses, so people want small allocation. That's why people like /24s, because they're easy to think about, even though people really shouldn't be using them in BGP. And it's expensive. It's expensive to get anything bigger than /24. But people, it's not really a choice. It's not worth making everyone else's life harder just so you can have your smaller prefix. And you work with other people for that. Let's say you're announcing a route. You withdraw it, so you say no more route, and then you announce it again. This is bad. because it's called route flapping. And it ripples the entire internet and takes a lot of CPU, and it's very confusing and it can cause a lot of problems. And so you have what's called route flap damping, which should solve this problem, right? You penalize routes that flap, and if they flap too many times in a certain time period, you say you don't get to be a route anymore, and you wait for half an hour normally before it fixes itself. So for every flap you got a penalty, and then you exponential decay. So you have you can tune the half-life. That's the knob you tweak. And then if it's above the suppress limit, you don't advertise it to peers. And then you re-advertise it once it's should be below the reuse limit. Basically, that way you don't end up flapping with your route flapping dampening. Here's the thing: it's actually worse than nothing. It's not a good thing because it's inconsistent amount of the restrictions and the weights. Not the weights, the thresholds. And vendor defaults also, they actually tend to suck. The vendors like Cisco and Juniper, they way too aggressive. And downstream, if you consider you'll have multiple paths or anything downstream, they'll see up and down could happen a whole bunch, and they then think it's even more flapping. And then you end up having a really bad quality of service and quality experience problems. Just have race conditions, again, where things are in the wrong order, you end up having what seems like more flapping. So don't use route flap damping. Probably difficult to say. It's actually much worse. It was a thing people liked, I think, in like the 2000s, and then they realized it actually sucks. You have aggregation. Again, the internet's growing, believe it or not. It's a big thing. And every route is an increased cost for everyone who runs BGP, which is every network, because there's more things to keep track of. You have a big list. And most people could really be using fewer routes than they're actually using. Like, most people are actually not being that efficient, which is really unfortunate. But it's hard to incentivize people. There's no incentive on an individual scale to do smart routing. As long as it works, it works. So aggregation in practice, ISPs should aggregate their consumers whenever possible. So if they have overlapping, if they can combine their announcements into one announcement, they should do that. They also, doesn't mean smaller notifications are bad. They're still okay. In fact, they're required, but they should be kept in iBGP, kept internally. And then this benefits everyone because route aggregation reduces downtime, and also makes everything faster and easier and less expensive, and benefits everyone involved. It even helps the customer if they set it up correctly. So, it might seem at this point BGP is effective, but it's kind of complicated, and there's another question of, is it efficient? And surprisingly, actually it's very efficient, which for such an old protocol that's basically just been kind of bodged together through the 21st century, is actually a bit surprising. The mean length, the mean number of AF hops is 5.5. If this thing will update, thank you. So you have to go through 5.5 networks on average to get to any other network on the internet. And it's actually been decreasing recently as well. I will say that mean path length isn't the best way to say like the efficiency, but it's an easy one, and there's not actually a great way to measure it. But it works really well. And actually, the mean path length has been decreasing recently. I think since like the around 2017 looks like it's been going down. But that being said, behavior is very dependent on part configuration. If you misconfigure something, you could cause a lot of problems, a lot of outages, a lot of security issues, a lot of other problems, quality of service. Again, back to multi-exit discriminators we talked about earlier. It's used as a tiebreaker. If you have things that look the exact same, it's a tiebreaker. And it shouldn't be transmitted over eBGP. That being said, actually often is, because ISPs will use a multi-exit discriminator to kind of hint at what you might want the path they might want you to use, but it's kind of iffy. And it's optional, and there's no standardized scale, which it means it's very hard to work between different vendors. And it can really affect the quality of service or quality of experience. If this gets messed up, you end up picking a route you don't want, especially if you have two routes going to two different vendors. That can be very confusing because the scales will be completely wrong. I talk about security considerations. BGP security. In original notification, there was no ownership verification. And this actually worked really, really well. There was only a couple of incidents. It really never went wrong. There was never a situation in which a big ISP caused problems. That's wrong. That's a lie. No, it went wrong very frequently because once the internet got big and not more than just a couple of universities across America, run by the Army or the DoD, people started doing bad things, and there's lots of money that was involved. YouTube was down. One of those might be more important than the other one. And so it's BGP hijacking is what it's called. And it's a really complicated process. I'm going to try and explain it simply. Okay, you, the attacker, announce a more specific prefix than the other person, then you profit. It's not very complicated. It's stupidly simple, which is why it happened a lot. Now, something like HTTPS makes that less of a problem because most clients just won't connect anymore if it's not authenticated correctly. But if you can still cause problems, not everything is TLS, much to the chagrin of CSIC majors. So to solve this, you have the RPKI, the Resource Public Key Infrastructure. The name is actually not very descriptive, but it is TLS certificates for signing, but for BGP. That's what I wrote. And it's the default on most new deployments, especially IPv6 deployments. If you don't know IPv4 or IPv6, IPv6 is newer but less common, and people are scared of it because they can't do networking. In IPv4, it's not widely deployed. You can use it, just no one wants to do work, quite frankly. No one wants to do extra work to do security, at least not yet. And if it's used correctly, it can have a significant, make it significantly more difficult to actually do BGP hijacking. It's not foolproof, but it's pretty good at what it does. It's again, it's not perfect, but it's pretty good. And one thing it does not encrypt anything. It only does signatures because there's no really need to encrypt it because it's all public information anyway. So how does RPKI work? So regional internet registries, or RIRs, they sign certificates for an AS or an ISP. Again, this is all very analogous to TLS. RIRs are kind of like a CA or a certificate authority. You have route or origination authorizations, or ROAs, which determine who can answer what prefixes. And basically, you sign those with the certificate, with the keys and certificate. And then, to be a bit more specific here, in all compliant peers who follow RPKI, they keep an updated list of ROAs. And they reject any malicious announcements. So you can, so that if someone is invalid, it doesn't cause problems. One thing to note is that most ISPs are actually local internet registries, and they assign their IP addresses to customers, both in data centers and in non-data center applications. And some ASs choose to connect directly with an RIR, but small networks usually just say that their ISP should deal with it, and it makes more sense. And another interesting thing you can do, you can use BGP for DDoS protection, or you can use it as a tool. Basically, you announce new routes, which act as the DDoS mitigation. Basically, you say, hey, instead of going to my data center, go to my something else. Instead of something like Cloudflare, for instance, where you would just be changing the IP address in DNS, for instance, this actually is going, botnets very rarely can control the BGP routes that they're using. So, and therefore, those mitigation servers will pass traffic to the legitimate servers. It's also very difficult for attackers to influence the routes, as I mentioned earlier. Oh, that's nice. Okay. And has less of an impact on real customers. If you're a real customer, you just get passed straight through. Now, a couple of resources if you want to look at more inside of your home, if you want to look more at this later. There's DN42, which is a hobbyist virtual networking, basically doing BGP over VPNs, over private IP spaces. If you want to learn how to do that, and if you think you're not qualified for this, I'll let you know. The first person I contacted with DN42, they were 15. So no, it's not complicated. Anyone can do this stuff. There's also NANOG, the North American Network Operator Group, and RIPE and APNIC. They all have pretty good things on BGP. They have presentations, sort of like this one. There's Hurricane Electric. They have they don't only people who provide BGP stuff. They provide a decent interface, and they're a lot of different data points. And there's Cloudflare's blog. I don't really like Cloudflare all the time, but they actually do a decent job at writing blog posts normally. With that in mind, any questions?
I have a question.
Chase?
So, is there any way BGP can be used to find a route for this lanyard to you?
That'd be very complicated, but if you have a direct connection, it's very easy.
Oh yeah, I was going to tell you about it. I can take them out.